Chem 1A, this is Chapter 5, Lecture Video 4, and we're going to be discussing gravimetric analysis, which is a pretty cool thing. It's often used to determine the amounts of substances present in a solution when we don't know how much. One of the easy applications of this technique is with measuring whether water is safe to drink or not. If you know there are, for instance, heavy metals present in the water, like lead, which is toxic, you can measure how much lead is actually present because there are safety guidelines for this, right? Having zero lead in our water, there's probably a tiny trace amount of lead in most of the water we drink, but as long as it's below a certain threshold, it's safe. So determining whether we're at that threshold, above that threshold, or below that threshold of what's safe is very important, and gravimetric analysis can help us determine, hey, how much lead is in our water? So let's say, for instance, I have this solution here, and it contains sodium sulfate, and I don't know how much, but I know it contains sodium sulfate. Well, what gravimetric analysis is all based off of is pretty much the solubility rules and precipitation reactions. So if I know there's sodium sulfate in that solution, I need to find another ionic compound that when I add it to sodium sulfate will form a precipitate. And the less soluble that precipitate is, the better, right? So barium sulfate, according to our solubility rules here, let me use a different color. Barium sulfate, according to our solubility rules, is super insoluble. So what can I add to sodium sulfate to get me barium sulfate? Well, technically, any soluble barium ionic compound is going to be fine. Let's say, for instance, in this case, we'll use barium chloride. All right. So it could have been barium bromide. It could have been barium nitrate. It doesn't really matter as long as it contains barium 2+, because I know that when barium 2+ comes in contact with that SO4 2-, it's going to precipitate as a solid. So what happens next is we take this solution, we start adding it into our unknown solution, and we don't really care how much we add. We can just add as much as we want. And we want to add in excess so that the barium chloride is our excess reactant and the sodium sulfate is our limiting reactant. So as you can see, as we add the barium chloride to the solution, you start seeing a white precipitate form in the solution, and we can measure how much precipitate we make, right? And you just keep adding until the precipitation reaction stops occurring, right? We keep adding the barium chloride until no more of our solid is formed. At that point, we can filter it and collect the solid, dry it, and then weigh it. And once we've weighed it, we can use that information to back calculate how much sodium sulfate was originally present. So let's do an example problem of that. So let's say we have a mineral. We're geologists now, and geologists have weird names for their minerals, and I have no idea how their naming systems work, but they have a mineral called thenardite, right? And it contains sodium sulfate along with a bunch of other inert compounds. So effectively, we're going to be focusing on our sodium sulfate and the fact that we have a 0.123 gram sample of the mineral. We want to know what the percent mass of sodium sulfate is in this mineral. So what we do is we do gravimetric analysis. Just like in the previous picture, we're going to add barium chloride because we know barium chloride, when added to sodium sulfate, will form a precipitate, being barium sulfate. And so we add barium chloride in excess until all of the sodium sulfate has reacted. Once we do that, we filter it, dry it, collect the barium sulfate we form, and measure the mass. And we get 0.177 grams of barium sulfate is present and recovered. And we want to know what the mass percent of sodium sulfate is in the mineral. So let's break this down, right? How does this all work? Well, there's a precipitation reaction going on here, and we need to write it out, predict the products, balance it, and do all that fun stuff, right? So we have sodium sulfate reacting with barium chloride. This forms barium sulfate, which is in the solid state according to the solubility rules, and sodium chloride. In order to balance this reaction, we got to put a 2 in front of sodium chloride. And this is pretty much everything we got. We know over the course of the reaction, we collected 0.177 grams of barium sulfate. We know that in the mineral in total there was 0.123 grams of the mineral. Now, I know that all the barium sulfate came from the sodium sulfate. All the sulfate in barium sulfate came from the sodium sulfate. So next, we need to calculate grams of sodium sulfate, because if I want percent mass of Na2SO4 in my mineral, well, that's really just equal to the grams of Na2SO4 over the total grams of the mineral. Which we know is 0.123 grams. And then this is just times 100 to get it in percentage units. So really what I need to know is this value. How many grams of sodium sulfate were originally present? Well, that's a stoichiometry problem, right? We have 1.77 grams of BaSO4. We need to get, hey, how many grams of Na2SO4 are there? Now, before we can do that, we need to get moles of barium sulfate. So let's calculate the molar mass, and that we can use to get moles. So if we calculate the molar mass of barium sulfate, we get 233.38 grams per mole of BaSO4. All right, so we can see that the grams of barium sulfate are canceling and we're left with moles. Now we need to use a mole-to-mole ratio. We know that according to our balanced chemical equation that 1 mole of barium sulfate is formed from 1 mole of sodium sulfate. And then finally, the last step, we need to multiply by the molar mass of sodium sulfate, which if we calculate, we know is 142.04 grams of Na2SO4. I'm just going to erase this a little bit here, per mole of Na2SO4, right? So moles of Na2SO4 cancel, barium moles cancel. And so if we do this calculation out, we can get how many grams of sodium sulfate were in that original mineral compound. And so what we get is that in that mineral, originally there were 0.108 grams of sodium sulfate. And finally, so if we want the percent mass of this compound in the mineral, we just need to go, okay, great, well, our percent here is going to be 0.108 grams of Na2SO4 divided by the grams of the mineral, 0.123 grams of mineral, times 100 to get into percentage units. And if we calculate that out, we get 87.8% by mass. Now, this technique is super useful. It's used in very significant numbers of applications, right? From water treatment analysis to mineral analysis, like in this example, to so many applications. One of the best parts about it is it just involves limiting reactant stoichiometry or stoichiometry in general, where we're going from the product back to one of the reactants and figuring out how much there was of that thing. The difficulty in it for students is that literally the reaction could be any reaction we want as long as it forms a solid, right? So any of our precipitation reactions are fair game for gravimetric analysis. And part of it is determining what reactants do we need to put in there to get a precipitate in the first place. All right, if you have any questions, please let me know. And yeah, contact me via email or Zoom.